Hey there and welcome. Today, we're going to pull back the curtain on the one piece of tech that honestly makes our entire modern wireless world tick. It's called orthogonal frequency division multiplexing, or just OFDM for short. And believe me, it is the unsung hero behind your Wi-Fi, your 5G, pretty much everything.
Okay, so let's think about this for a second. Have you ever really stopped to wonder why it's so hard to send a massive amount of data through the air? I mean, you're streaming a 4K movie, you're on a crystal clear video call. That's a ton of information flying around. Why is that such a challenge? It's not like the air is a nice, clean copper wire, right?
Well, the biggest problem, the real villain in our story, is something called multipath interference. See, when your router sends out a signal, it doesn't just go in a straight line to your phone. Oh no, it bounces off everything: walls, furniture, even people. All these little echoes and reflections arrive at your phone at slightly different times, and they just jumble up the original message into a big, confusing mess.
So, how in the world do you fix that?
Well, the old way of doing things was like trying to shout one really long, super fast sentence in a big, echoey room. It's a disaster, right? The echoes would garble everything, and if just one part gets messed up, the whole message is basically lost. But the new way? It's so much smarter. It's like having a whole crowd of people, where each person says just one word, nice and slow. Even with all the echoes, it's way easier for you to pick out each word and put the full sentence back together. And that, right there, is the core idea behind our hero, OFDM. Instead of trying to send one huge, fast, and really fragile signal, we send hundreds, sometimes thousands of tiny, slow, and super robust signals. It's a simple idea, but how it's actually pulled off, well, that's where the genius comes in. All right, so how does this actually work in practice? Let's follow a little chunk of data on its journey, all the way from the transmitter to your device, and see how OFDM handles the whole thing. First up, at the transmitter, it takes that big, high-speed stream of ones and zeros and splits it into a whole bunch of slower streams. Next, each of those slow streams gets encoded onto its very own little radio wave, which we call a subcarrier. Now here comes the magic part. A really cool mathematical process called an inverse fast Fourier transform, or IFFT, cleverly bundles all of those subcarriers together. And finally, a little buffer, a guardrail called the cyclic prefix, gets tacked on to protect the data from all those echoes we were just talking about. I really want to hammer this home. That IFFT step is absolutely crucial. It's not just a minor detail, it is the mathematical heart that makes OFDM possible. It's the secret recipe that arranges all those hundreds of subcarriers so they can be packed incredibly close together without just turning into a chaotic mess. It's a total masterpiece of signal processing.
So what happens when the signal gets to your phone? Well, basically the exact reverse process. First, it chops off that protective cyclic prefix. It's done its job. Then the fast Fourier transform, the FFT, does its reverse magic. It neatly unbundles that complex signal and separates out every single one of those individual subcarriers. Finally, the little bits of data are pulled off each subcarrier, and all those slow streams are stitched back together into the original, perfect, high-speed message. It's amazing.
But hang on a second. If all these signals are packed so incredibly close together, how do they not just crash into each other and interfere? Well, that brings us to the real secret sauce of OFDM.
And the secret has a fancy name: orthogonality. It's this beautiful property from mathematics. And what it means, in plain English, is that even though all these signals are technically overlapping in the airwaves, your receiver can still tell them apart perfectly. Zero interference.
I mean, just think about that for a second. They overlap in frequency but do not interfere. That almost sounds like it breaks the laws of physics, doesn't it? How can two things be in the same place at the same time and not mess each other up? And here is the aha moment. It's all about perfect, clever timing. The math is designed so that at the exact split second your receiver is measuring the peak of one signal, all the other overlapping signals are perfectly at a value of 0. They contribute literally nothing to the measurement. It's like they're invisible to each other for that one critical instant. It's just so clever. So this isn't just some neat math trick for a textbook. This elegant solution is the engine that powers our entire connected world. Let's talk about why this matters so much to you and me every single day. Of course, like any technology, it's a game of trade-offs. The advantages are huge. It's incredibly efficient with our limited radio spectrum, it's naturally tough against that multipath problem, and it's fantastic for high data rates. The downsides? Well, it needs very, very precise timing and can be complicated to build in hardware. But as you can probably guess, the benefits have totally won out. And here's the proof. This isn't some far-off, futuristic concept. OFDM is the beating heart of your Wi-Fi. It's the engine behind 4G and 5G on your phone. It's used for digital TV, your home broadband internet, and even for communicating with satellites. It is, and I'm not exaggerating, everywhere. So when you boil it all down, the genius of OFDM is this one simple strategy. Take one massive, complicated problem and break it into a whole bunch of small, manageable ones. That single idea completely changed the game for wireless communication and literally built the connected world we all live in today. And it really makes you wonder, doesn't it? What other simple idea out there right now is going to be powering our world tomorrow?